If you can't explain it to a fourth grader, you probably don't understand it. Hello, everyone. Welcome back. Today, we're going to continue on this idea of being able to explain and convey something that's very non visual, non tangible to most of us, to something that we can understand and grasp. And Einstein's quote, which I kind of butchered, was the idea that if we can't really simplify something, then probably we don't understand it. And whether or not that's true, the purpose of this talk is to try to take a raw idea, like how does a radio work, and explain it so that almost everyone can understand it. And of course, this is going to be quite challenging, but we're going to do this in a very informal way. So obviously, if you were to do this as a speech, you could really go deep and think about how to do this very, very effectively. But let's just try to do this in a very informal talk. For example, how could I explain how a radio works? Let's start. Let's try this. So, the first thing that we have to understand is that magnets and electricity can influence each other. Have you ever heard of a wire connected to a light bulb? And if you move like a ring magnet through that wire, it will start pushing the electricity in the wire back and forth, and your light bulb will start flickering on. And the more you shake that magnet, the brighter the light happens, and the slower you go, the dimmer the light becomes. And that's exactly how a microphone works. You have a coil of wire connected to your circuit, and that coil um, is wrapped around this magnetic rod, and then that coil is also connected to a thin film. If I were to speak on the sender side and say hello, the film would start flapping, and that would cause the coil to move back and forth along the rod, and that would induce back and forth electricity along the circuit. If I were to speak in a high pitched voice with a lot of frequency, it would start moving back and forth a lot faster. If I spoke with a low pitched voice, it would go slower. If I spoke loudly, right, the amplitude of that thing would also be higher. Okay, I guess the force of it pushing would also be higher, and if I spoke softly, the voltage would be lower. So this is the idea of how do we get our voice into the wire of a circuit, and it's through the use of magnets and a flap. The next question is how do we now do we add this to what we call a resonance frequency or a carrier frequency? So let's talk about what is a carrier frequency for the first time. Have you ever heard of a tuning fork? And the tuning fork shakes, and when it shakes, it can cause other things to shake, like a glass or another tuning fork. It's a lot like, for example, the analogy of a swing, right? If in this case, the tuning fork is pushing air back and forth. And if you think about a person on a swing, if you push in tandem with the same frequency as the swing will keep on going and may even start swinging more and more. Whereas if you have the wrong timing, you start pushing against the resonant frequency, and now things stop moving. And this is the idea of a radio. We're going to be sending over the air these vibrations, but they're not vibrations in terms of mechanical vibrations with our voice of air going in and out. We're going to do this with something called electromagnetic fields. As we said before, um, we can convert this back and forth of electricity into magnetic field, just like the magnetic field influencing the wire or the electricity in the wire, we can influence magnetic field by pushing things through an antenna. And we do this with a carrier frequency. So what does this mean, a carrier frequency? The carrier frequency is going to be a sound that has a much higher frequency than my voice. Even my highest voice will be very, very slow compared to the carrier frequency. So for example, if the carrier frequency is like, and my message is, my name is Jeremy, the carrier frequency will combine with my voice would sound like, right? It's like my signal combined with a carrier frequency. And we'll talk about how that's mixed in a future lesson. But basically, there's a way of using um, an oscillating circuit to mix the carrier frequency with my voice. So now you have on this circuit a signal which is represented of voltage, of pressure going back and forth, right, and of current in a way, right, going through this circuit. And then, I mean, there's things like amplifiers and other um, components in a real practical circuit, but in a very simplistic terms, this is now going to be sent across an antenna. And as mentioned before, the antenna is like a long wire, and if it's powered by something, it's even more powerful. But we'll get to that next time. It's like a long wire, and as this wire is pushing and back and forth electrons in a way, not really electrons, but the phenomenon of electricity back and forth, this wire, it's sending out electromagnetic waves into the air. And so now we have to think about the other side, the receiver side, right? What's happening there? So just like the tuning fork, we need this idea of a way of capturing the 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 resonance, or we have to get this thing to have a resonance as well, to actually shake with what's happening with that carrier frequency out there. Because what's happening realistically is that everybody is sending out something, right? It would be wonderful if in the universe there were only two people, me and you, right? One sender, one receiver, then we wouldn't really need a lot of things here. But if everybody's sending with their own carrier frequencies, if Jeremy's sending, my name is Jeremy, and John is sending, my name is John, and Dan is sending, right? And everybody's getting these messages on the receiver side. When we combine it, it's going to sound like, right? Like white noise. We won't be able to receive the actual message. So upon receiving things, we need to be able to tune just the carrier frequency we're interested in. So once again, we're getting all of these signals through our antenna. Is um, our antenna is receiving all of these things, and the back and forth of magnetic fields is causing all kinds of spikes and divots and shapes inside our antenna, which now affects the wire inside our circuit. And then we have back and forth at different rates of so many things, so many signals coming in. And we now need to tune. We need to tune to the carrier frequency that we want. So how do we do this? We have something called a tank circuit or LC circuit. The idea is that we have in parallel one capacitor and one inductor. I mean, in a practical circuit, it's very different. But for sake of the most simple circuit, how is it done? We have one capacitor and one inductor. And if you remember the last talk, we talked about an inductor. An inductor is like a water wheel, right? A water wheel. What happens is when we have water going inside there, initially the water wheel adds inertia. It resists. It resists, right? It gets back pressure or back voltage, resists the flow of current, of electricity, or if we think about water wheel, water. But eventually, if that water is streaming a nice steady way, like direct current, eventually it continues. And if you turn off the tap or we open a switch, that thing will continue to turn and continue to cause current for a while before it slowly winds down. So you can think of the inductor or the water wheel as a source of pressure, right? Or source of resistance or pressure, or source of inertia, right? Source of voltage. And if we look at the capacitor that we talked about the idea that um, it was a lot like in the water park when you blow or push uh, water into the tank, it slowly drips, drips, drips. So things continue flowing, working as normal until you reach the top of the bucket and suddenly you reach capacity and nothing flows anymore. So it's kind of like the idea is if we're too steady, everything will eventually stop. But when you turn off the tap, the water wheel eventually tips and back flushes everything out. Right? And we said that's our same idea of this capacitor with two plates. The charge builds up on a plate and it wants to go to the other side, but it can't. And eventually, when you turn off the power or the electricity, right, the charge flows or the current flows back out. So you could think of the capacitor as kind of a source of current. Now, if you combine these two things in parallel, and you add a little bit of current inside there, you can think of the idea of the bucket filling up and then eventually tipping over if tuned properly. And then this water wheel will start turning and fill it to the other side, and it will go back and back and forth in resonance. But that's not what I want to talk about. I got sidetracked. Let's talk about this idea of a carrier wave. So if I have three senders, we have Tina, Jeremy, and John, right? We have three different signals with three different carrier frequencies. Now, what happens when Tina's high pitch carrier frequency is sent over to my tuner that's tuned for my voice, right? I don't want to hear Tina's message. I want Jeremy's message. Well, imagine because Tina's carrier frequency is so fast, it's inducing, right, a signal that's also very fast in this uh, inductor capacitor tank circuit. So if you go back to our water analogy, what happens if things go drip in and out very, very fast? I'm sucking and blowing very fast, and I have a bucket inside here. We talked about this before, right? If you keep on dripping, and then suck it before you reach the top of the tank, the tank will never flush, right? Things will just come into the tank, empty the tank, into the tank, empty the tank, and it will never go beyond that bucket. Likewise, if you think about that water wheel, we talked about if something's going in and out too fast for the water wheel to react, eventually it's going to be like a closed circuit. It's going to be like a barrier, like a wall, because we never get enough steady current to let the water wheel move, right? It's always going to be pushing back and forth, and never let anything flow. So if you think about it, Tina's message, because of this capacitor inductor combination, will never go to the rest of the circuit to process. That the effects of her voice, of her signal, will never go through this combination. Now let's think about John's example. John has a really slow resonant carrier frequency, right? So how does the resonance that exists in our inductor capacitor stop his situation? Well, we talked about it, right? If something is almost like DC, moving too slow, the capacitor suddenly just gets locked in the field's position and nothing goes beyond it, right? And we also talked about this in the water wheel example. If something is too slow, the capacitor will keep on pushing, and will continue putting pressure, so that when you want to, I guess, suck and go the other way, you still have some something happening. So you're never going to get the signal passed. That the bucket will be locked in the wrong place, or we'll be having like a flushing effect that's overriding what's coming into the from the antenna. And if you think about this analogy with water, it kind of gives us an intuitive understanding of how a radio receiver tunes out the voices or the signals from different carrier frequencies. Whereas if the tuner matches my signal exactly, then it will carry through, right? Because the buckets and the water wheel will be assisting the flow instead of fighting the flow, just like that, pushing against the swing. So the next point is that, well, on your, for example, car radio receiver, you have a tuner, right? And this is the idea that you can change the characteristics of your tank circuit. So, for example, you can change the material uh, and the magnetic material in the middle of your inductor. You can change the number of windings in your conductor. You can change the material inside of your capacitor. You can change the plate size of your capacitor. You can change the distance of your capacitor. There's so many ways to physically change this tank circuit. But that is, in a nutshell, how we tune out the millions of voices and just capture what we want from our sender. After that, we have this idea of maybe a diode. So maybe after we go through the tank circuit, the signal, the pulses go beyond, and then we have maybe a diode, which we talked about being like a one-way flap. So, for example, with the carrier frequency, we might have back and forth. How do we cut it off and just have the positive part of that signal? So maybe we just want this kind of motion, but we don't want this kind of motion back and forth. We use a diode. Following that, we have the idea of we now have just Jeremy's signal, right? But we want my name is Jeremy. How do we get rid of the carrier frequency? And we just said that the carrier frequency is much, much, much faster than my voice, even my highest pitch voice. So we have something called a low pass filter. And basically, it's just, again, particular capacitor and a resistor. And what happens is, if you think about this bucket analogy, the carrier frequency is moving very, very, very fast. It's going back and forth, or chopping back and back and back, or nothing and something, nothing and something, nothing and something. And we want this to be my original voice without this choppiness. So what happens is the capacitor, like a water tank or bucket, holds in the charge, right? And when the carrier frequency was chopping in, it fills up the bucket. And when the carrier frequency stops, it fills it back. So now everything will now be smoothed out because the charge is filling in what the carrier frequency was usually pumping in and out. Now it's just nice and steady. And now my voice is restored to I am Jeremy. Finally, to wrap up everything in this complex, but I think graspable and intuitive way of thinking about radios, is the speaker. So now that we have my voice represented in a nice, smooth way, we can now push it through a coil. The coil will be wrapped around a magnet, which is and the coil is connected to a big flap or a diaphragm. And as the signal moves strongly, it can make a loud sound by pushing hard. By going fast, it can make a high-pitched sound. By going slower, it can push air in a lower frequency. And there you have it. My impromptu, unplanned attempt to describe how radios work using a very simplified analogy of water circuits and tuning forks. So I'd like to hear what you have to say about something complex. Can you describe something that is unseen using analogies and figurative language? Can you make it something that people that don't have the same background as you understand? Please try and include your post below. I enjoyed this, and I'll see you next time. Bye.